So let's look at some reaction stoichiometry. So let's remind ourselves firstly in what we covered in the previous theme. In the previous theme, we looked at right and balanced chemical equations. So in other words, we know how to balance chemical equations, we know how to write them, how to predict products, and go from there. This theme, however, is all about once you now have a chemical equation, how can you predict what the mass is of a product that you will form? If you know, for example, if you mix two masses of reagents, what kind of mass of product will you form? If you know how much product you want to form, what mass of a reagent do you require? And how do you connect those concepts? And that links all the way back to something that you might have encountered before called stoichiometry. Right. And stoichiometry links to the concept of moles. Okay. So I want to start the conversation with something maybe a bit different, or just a step back. And how does moles and masses link or differ? So if we think in terms of, atoms, mole, that's a bit high, but that's fine, and mass. Right, let's compare these three concepts and look at this chemical equation that I have here. So it says phosphorus reacts with chlorine to give phosphorus trichloride. So basically it says so in terms of atoms first, let's do atoms first. It says 4 phosphorus atoms, right? So you can see there's a little 4 there. It says 4 of them reacts with 6 times 2, so 6 times 2 chlorine, so that makes 12 chlorine atoms to form 4 times 1 phosphorus plus 3 chlorine. So that means 4 times 4 atoms, so to form 16 atoms on the right-hand side. And if you quickly notice there, we can then say, well, it means there's 4 atoms of phosphorus plus 12 chlorine atoms, which forms 16 other things, or 16 atoms. So in terms of atoms in a reaction, there's always balance. Right, so 16 atoms on the left-hand side will always give 16 atoms on the right-hand side. That's something you can go and count, because you balance a reaction as such. You won't have more atoms on the left-hand side than there are atoms on the right-hand side. The same goes for the mass. If you combine 124 grams with 425 grams, then that will produce 549 grams. That's the law of mass conservation. Same idea of reason why the atoms balance. So these things tell us in terms of chemical equations that those things are always equal. But what do you notice about the number of moles? In other words, the numbers that are here in front of your reagents and your product. So it says 1 mole of phosphorus reacts with 6 mole of chlorine to produce 4 mole of phosphorus trichloride. What happens if we want to sum these? You will notice 1 plus 6 does not give 4, right? So, that equation is not satisfied. And, in principle, that the reason is because these things do not have the same molar mass. They don't have the same ratios. So, and that's exactly the mole concept. That's the stoichiometry concept behind it. So that means we actually need to look at those numbers as a ratio concept. It's not a sum, like law of mass conservation. It's to give us the ratio in which things react and form. So it means 1 mole of phosphorus reacts with 6 mole. It's not a sum anymore, it's a ratio. So it means kind of like a divide. It's as you would say, if you have a ratio, so meaning you say P4 ratioed to 6Cl2. And in mathematics, that means like we divide. So it means you will later see how that links back to the concept of your dimensional analysis. And now it will be useful to think of it as such, because it gives us a ratio to work with. It's 1 to 6, 6 to 4, 1 to 4. So your chemical equation in terms of number of moles is a ratio. So that's a very important concept. Okay, right. So let's look at an example. Just remind ourselves of the basics of stoichiometry. They should be familiar with, something that you might have seen before from even your school days. So it says glucose reacts with oxygen to give CO2 and water. What mass of oxygen in grams is required to completely react with 25 grams of glucose? What masses of carbon dioxide and water in grams are formed? Okay, so a basic question, meaning we're given a reactant, we're told it reacts with oxygen, and we're given the two products. And we're asked, what are the masses of the other stuff? And we're given one mass of the one reagent. So what do we need? Our first thing is we need probably a chemical reaction, so an equation to deal with. So let's start by writing the glucose. So this is glucose, we're given the formula, right? And this is sugar, so it should be a solid. Reacting with O2, which is a gas, burned, so it's a combustion reaction, to form CO2 gas plus H2O gas. All right. The phases here aren't too important. This is just for you to balance. All right. Notice I said balance because we need to check that, right? So immediately you should notice, remember your order in which you balance things from your previous theme. So let's start with the carbons, would be the easiest. You see, we notice we probably need 6 carbons on the right-hand side, so that's a 6 there. And then you should also notice that, well, once we have a 6 there, we also need a 6 for the hydrogen, and then we can actually just put a 6 there for the oxygen. It will be the easiest to balance that. All right, and then it's balanced. It will be a very simple one. All right, cool. So theme 7 deals with the balancing. You can revise that quickly on your own time. Cool. So now we have a balanced chemical reaction. Remember, just in terms of your balancing, you'll always go carbon, oxygen, hydrogen, or carbon, hydrogen, oxygen, XHO. In terms of your balancing, you have your steps that you need to go through, which makes it a bit easier. Okay, so now we have a balanced chemical reaction. We're given the mass of glucose, and we're asked what mass of oxygen is required to completely react with this mass. So a good place to start would be then to determine something about the glucose, which would give us information about the oxygen. And remember, chemical equations, we cannot do anything with masses. We can only do something with the number of mole. So we need to convert this mass of glucose to the number of mole of glucose. So that would be your starting point. So it would be C6H12O6. Need to convert that to number of mole. We're given the mass, so that's 25.0 gram, C6H12O6. And now typically, you can remind yourself that, well, to convert a number of moles or to get number of moles, you would say mass divided by molar mass, right? That's how you want to do it. But the dimensional analysis method, you remind yourself that it is the same as saying 1 mole of glucose, C6H12O6, weighs 180.2 gram, or contains 180.2 C6H12O6. Right. So it is exactly the same thing as that equation. You want to cheat, and you can quickly write that down for yourself. But remember, there's 1 mole of glucose weighs 180.2 gram. Okay. That then gives us some value of 1.38 and some numbers, mole because that is what's left over, C6H12O6. All right, so this should be where you get to right now. Remember, to get the molar mass, you just sum the individual molar masses of 6 carbons, 12 hydrogens, and 6 oxygens from your periodic table. All right, so now we have the number of moles of glucose. What can we do with that? From that, we can then relate that to the oxygen in some manner. But what can we extract from our chemical equation? So remind ourselves that 1 mole reacts with 6 mole of oxygen. So I have a kind of hybrid method of writing that. So I like to say, well, our chemical equation tells us that 1 mole of glucose, 6H12O6, has a ratio to react with 6 mole of O2, right? That is what our chemical reaction equation tells us. And remember, I substitute the plus for a ratio sign, so like the double dots, because when I'm working with moles, then I work with a ratio. Okay, but what information do I have at the moment? Let me put that in blue. I'm just going to make this one smaller. I have the information that I actually have 0.138 mole C6H12O6. And I want to know something about the number of mole of O2. That's what I want to determine. I want to know how many moles of O2 will react, because from the number of moles of O2 that needs to react, I can get the mass of O2. Okay. Now you will remember, maybe you did this in school, maybe you had some interesting teachers. You did something like you had a cross multiplication, and then you divided some stuff. So you cross multiplied. So then you should get, on the left-hand side, you will get 1 mole C6H12O6 in O2. I'm actually just going to move it here to the bottom, because there's a lot of writing to do. Oops, C in O2 equals 6 mole O2 multiplied with 0.138 mole C6H12O6. All right. So I hope you've gathered thus far. All I've done is I've written the ratio from the chemical equation. Then I said, well, in reality, what we have is we have so many moles of glucose reacting with an unknown amount of O2. Sometimes you call it X, right? But I like my symbols, so I like writing in the number of moles of O2. And then we solve for O2. So in other words, we divide here with 1 mole of C6H12O6. We have to divide on both sides with that. So I'm going to rub this out. I hope you allow me to do that. So we're left with 1 mole C6H12O6. All right. And what do you notice now with your units? This unit cancels with that unit. Which gives us an answer for the number of mole of O2. And the number of mole of O2 is going to be 0.832 and some number mole O2. Okay. As you see, this unit, like I said, cancels with that, and you're left with something that expresses mole O2, like I have here. All right, so that's what you did in high school. In high school, you probably just said it's 6 times that number, and then you had a number in mole, but this is actually properly where the units come from. All right, so now we have the number of mole of O2. But what do we want? We want the mass of O2. And to get the mass, well, you can go through a whole rigmarole. So remind ourselves, mass would be number of mole times the molar mass. That's your little cheat that you can remember. But we want you to do it in terms of the molar of the dimensional analysis method. So you would say, well, it is 0.832 and some numbers mole O2 multiplied by the molar mass, but in principle there are 32.00 gram O2 per 1 mole of O2. That is a correct statement to do. It's the same as multiplying with the molar mass. You see, it's 32 gram per mole. Okay, it's the same thing. Then the mole units cancel, which leaves you with 26.6 gram O2. Okay. I'm running out of space, but it's just because I'm being very thorough in which I write for you. Okay, so we've done our first part of the question. What mass of oxygen in grams is required to completely react with 25 gram of glucose? Cool, so we've done that. Next part of the question. What masses of carbon dioxide and water in grams are formed? Okay, so it's the same question essentially. We just need to, or the same way to solve the question is now just for the products. So we can do the same thing like we wrote here. We see here, okay, if we compare, we see 6 mole of oxygen gives 6 mole of carbon dioxide, 6 mole of H2O. So if we write that in terms of a ratio, so then you would notice you get something similar to what we had. Oops, that's very ugly. Something similar to what we had here. So you can do it like that. But a very nice way to write it a bit more condensed, so you can go through those steps. We can immediately write and say, for example, the mass of carbon dioxide is equal to the number of moles of our glucose, which is C6H12O6, multiplied by the molar ratio. So in other words, there would be 6 mole CO2, which forms for every 1 mole of C6H12O6 that reacts. Right? I got that from the chemical equation. So there is 6 mole of CO2 for every 1 mole of glucose. But you can also, if you struggle, you can write it out for yourself, and then you get to this point, right? Because you will see it cancels out. So if you need to write it out, write it out. Okay. And then the final step is to multiply it with the molar mass of CO2. Okay. But in principle, what that is a unit conversion of the molar mass of CO2, which is 44.01 gram CO2 per 1 mole CO2. Okay. And let's just remind ourselves, I think this was 0.138 and some numbers mole. C6H12O6. Okay, so I'm not going to completely write out everything here. So you should then get 36.6 gram. And you notice that unit cancels with that unit cancels with that unit. So you're left with gram CO2. Okay, I hope that makes sense. You can, of course, always write it out in the same manner as we argued for the mass of O2. There's nothing wrong with that. You don't have to write it as condensed as I wrote it here. I just wrote it out because we went through the argument for O2. It will be the same argument for CO2. With good practice, you should then get 36.6 gram. All right. Now you can do the same for the mass of H2O. All right, so mass of H2O can be a similar expression to this. But what's a nice thing that you can use here? You can use mass conservation, right? Mass conservation. So if you use mass conservation, we know that 25.0 gram C6H12O6 reacts with 26, now that shouldn't be the rounded number, but 26 point something 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 gram O2 to produce 36.6 something 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 gram CO2 plus X gram H2O. All right, or you can call it the mass of H2O. So then all we need to do is we solve for this thing. Okay, so that means the mass of H2O is equal to 25.0 minus or plus 26.6 minus 36.6, which is equal to 15.0 gram. Notice everything is to three significant figures because of the three significant figures given in the glucose mass initially. Okay, so this is a basic question just to introduce you to the concept and to remind you of how to use the dimensional analysis things. And also I wanted to introduce you to remind you of this little idea here. Okay, I hope this helps. Then just in general about stoichiometry calculations, always remember, you cannot directly go from gram to gram. It's always gram to mole, then mole to mole through the ratio. So there's a ratio, and it will always be the ratio of the product or the thing that you want divided by the thing that you have. So that's technically this expression here. So like I have here, it's mole CO2 that I want divided by mole glucose that I have. The thing that I have at the bottom and the ratio that I want up top. Okay, that gives me the moles of the product, and then you take gram per mole, multiplies, in other words, it's molar mass, that gives you grams again. Okay, so that was the idea of this example, just to remind you of these basic things. You cannot move directly from grams to grams. It's always grams to mole ratio to mole, and then moles to gram again. So it's this iterative process. That's very important. Cool. I hope this was helpful and useful. I will see you in the next video. Thank you for watching.